This is part 17 of a series of many videos about parametric curves. We've been using parametric curves to model motion, and we'll continue to do that. We've been thinking about simple kinds of motion so far along a straight line, first at a constant speed and then at a non-constant speed. A couple videos from now I want to get into curved motion, and something that's going to help us think about curved motion is the idea of a vector. At the most basic physical level, a vector is just an arrow that we're going to imagine or draw or represent. And the simplest kind of vector to think about when you're thinking about motion is something called a position vector. Effectively, this arrow that we're going to draw, we're going to imagine to be a pen that is drawing the curve of motion. All right, so that's the goal, and that's actually going to be helpful to imagine. Also in this video, we'll continue with more on the fact that the area under the speed graph, when you start from time zero, that's when you start moving, gives you the value of the distance traveled function. If you're just starting to move at time zero, you also want to note that the distance traveled at time zero is 0. Before I get into those things, I want to clean up a few things. Down here, one thing I want to clean up is related to something I cleaned up a few videos ago. This equation for the tangent line to the distance traveled graph, initially I had a y right here, and then I changed it to the word distance. Why did I do that? The letter y is really representing the second coordinate of the motion. It's not a distance traveled, so it was misleading to call it y, so I changed it to distance. This distance is a variable, it's the dependent variable of this equation. But I just noticed that I forgot to change this to something else, so I will do that now. I could call it distance sub 0, but that would be a little misleading because it's not the distance traveled at time 0, it's the distance traveled at time b, so let me also change the 0 to a b. A second thing I want to do is just make a point of emphasis. Coming back up here, recall that in the scheme that we've been thinking about, we've created, first of all, a function h of t that allows us to change the speed of motion. H of t we've always picked to be a function that increases in value from 0 to 1 as t goes from 0 to 1, and this is just one example that you can use. The distance traveled function then was 5 times the speed because of this calculation involving the Pythagorean formula. And finally, we said the speed can be calculated from the distance function by taking what's called the derivative of the distance function. This prime is indicating that we're taking a derivative. The thing I want to emphasize here, well, one thing is that these functions, the distance traveled and the speed function, do have formulas. For example, what's the formula for the distance traveled function? It's, well, look at that. How about that? 5 times h of t, just like it should be, because it's 5 times h of t. It might be nice to multiply the 5 through the parentheses to distribute it through, and perhaps even expand this cubic here. Expand does that. There's a simplified formula for the distance traveled function for this particular h of t. How about the speed function? It has a formula as well. There's in the unexpanded form. I could also expand this. There's a simplified formula for the speed function. If you know some calculus already, you might want to check, compare these two functions, and notice the speed function is indeed the derivative of the distance traveled function. Another thing I want to emphasize is that the prime here is not the only way to take the derivative. It's maybe the simplest way, but there are other ways. For example, I can use a Mathematica command called capital D, stands for derivative or differentiate, I'm not sure which. They both basically mean the same thing. I can put the distance traveled function in here, put a comma and then a t, telling me that t is the variable I am differentiating with respect to t, so to speak. And if you enter this, you get the same thing we got before we expanded the last one. All right, so that's some things I wanted to tie up. Now let's get to the main content of this video. One thing I said was main content was that I wanted to add an arrow, a vector, a position vector, to the picture. I said that I want to imagine this position vector to be a pen that's going to be based at the origin. That will be the most useful place to start this pen. If the pen had an eraser, that's where the eraser would be, at the origin. And the tip is going to be at the point that is moving. It turns out you need to use graphics again to make an arrow. And instead of using line to make as we did to make a line, we're going to use arrow. There's a command in Mathematica called arrow. I need to use it inside this paraplot though, because I want the arrow to be in the upper left corner, which is where the parametric curve is. I already have a show command in here with a parametric plot and a list plot. Let me also add now over here graphics. Well, let's just start with a basic arrow. Graphics arrow. I want the arrow to start at the origin, so I put a 0, 0 in here, and end at the point where the person is as they move. Just like I have here and here, it'll involve C of H of something. In fact, C of H of B, because B is the animation parameter. I want this arrow to move as the point moves. Now I've got this entered. Let's go back down to our grid plot. And there you see already there's a black arrow pointing from the origin out to where the person starts. Now we let time go by. We see the person move. We also see the arrow change. Oops, got stuck. Okay, yeah, this is slowing down. It's going to speed up again. This is the motion that starts fast, slows down, then speeds up again. There is an instant in time where the instantaneous speed is 0, but theoretically the person is actually always moving to the upper left here, even though there's a time where the instantaneous velocity is 0. Speed is 0. All right, so that's how you add an arrow, and that will be useful to us. Again, imagine this is a pen based at the origin. It's tracing where the person is. It's tracing that red curve. Maybe we want to make the arrow red. To emphasize it's tracing a red curve, I can add some options in here like a thick, comma, red, comma, arrow. Now the arrow is red, and it is thick. I could also make it a thick black one. It was a regular black one before. I guess if I just get rid of red, it should be a thick black one. Yeah. Now you see it's a thick black one up in the upper left there again. That again is a position vector. To end this video, let's just do one more example to illustrate the main calculus concept. Again, that the area under the speed graph gives you the value of the distance traveled function. One more example to consider. Let's consider h of t to be, say, t to the third power. Why don't you guess what's going to happen here? Hopefully you guessed that this is going to start out slow and speed up. Starts out very slow, in fact, hardly moving. Speeds up. Is the distance traveled, the area under the distance traveled function equal to the, the area under the speed function equal to the value of the distance traveled function? Let's try a particular moment in time, like time equals 0.5, and see if we see that. Once again, the red curve is the speed curve. We see the area shaded. It's not quite a triangle. If it were a triangle, if I drew in a triangle here, it would have a base of 0.5 and a height a little less than 4. Looks like maybe 3.6. Multiply that by 1/2, you would get the area of the triangle. 0.5 times 0.5 times 3.6 would be the approximate area of the triangle. Now, of course, this region is smaller than that triangle, so its actual area is going to be less than 0.9, and the value of the distance traveled function is going to be less than 0.9. After, typed in 0.9. After 0.5 units of time. Yes, it is less than 0.9. Finally, I'll emphasize again that there is on the Mathematica palette here, there is a definite integral symbol here. Without knowing any calculus, you can just think of this as an operator that is going to give us the area under the speed graph between t equals 0 and t equals 0.5. I use this funny symbol, put the speed function there, put this t there, the variable that's right there, this should give us the exact same answer, 0.625. It's just an operator, an integral operator, that gives the area under that graph and therefore also the distance traveled. And with that, I'll end this video.